one of the grandson of Ugo Fano. Actually, I was graduate from Shin Watanabe and Michio Matsuzawa. And after that, I was working with Chidon Lin. Then I learned a lot of things from Ugo's sons. Then today I'm going to talk about this hyperspherical approach to 3 and 4 electron atomic system. This work is done with Chidon Lin. Then first I'll give a brief introduction and a hyperspherical method itself. Then most of my talk is about 3 electron system, about classification of triply excited states based on low vibrational motion, based on the low vibration motion of the 3 electrons based on a low vibrational motion. Then one is intershell triply excited states, where 3 electrons are almost the same distance from the nucleus. Then another one is intershell state, which is one of the electrons has a long distance than the other 2 electrons. Then I will show some preliminary result of 4 electron system, and I'll give a short summary. Then in the singly excited states, 2 of the electron is really occupied in the ground, the inner shell. Then only 1 is active. Then usually it's described by this independent particle model, 1s2 ml. Then in the doubly excited states, the actual 2 electrons are active now. Then there, independent particle model doesn't work. Then KTA, correlation quantum numbers, are introduced by many people. Then, and in the triply excited states, there, all the 3 electrons are in excited states. Then, completely independent particle picture doesn't work. Then, sorry. Then sometimes the most inner shell is open. Then sometimes it's called whole atom. Here is the experimental spectra of lithium triply excited states. Then, here 0 is the ground state of lithium. Then triply excited states is really far from this ground state of lithium. Then it goes through the double excited states, then far, and here is the triply excited states. It's about 150 eV. Then it's really above the threshold of lithium plus and the lithium double plus. Then these triply excited states can be decayed into both lithium plus and lithium double plus. Actually, there are to describe two-body systems, there are 2 types of separability of the variables. One is so-called mean field theory. The total wave function is separated can be described by the direct product of the one particle wave function. Then another one is so-called Born-Oppenheimer adiabatic approximation. There, it's the first, this separability is here. First defined by the slower variable. Then the other one is the channel function is the function where the fixed at the up the variable r. Then okay, here anyway separability is here. Then there, first we fix the shape of the few body system. Here it's 4-body system. Then particle is oscillate around the equilibrium position and rotate itself. Normally, atomic system is described by this Hartree-Fock type, this independent particle picture. But here, we try to describe atomic system by this von Oppenheimer type picture. In a hyperspherical approach and in the 3-electron system, there are 9-dimensional space. Then I separated into 2 parts first, then hyperradius and the hyperangles. The hyperradius is the most important variable in this approach. Then fixing like a moment of inertia. This is treated as an adiabatic parameter. Then the other 8 is we can take any combination of hyperangles. But here I separate further 2 parts. And one is the Euler angles, which describe rotation of the system. Then the other 5 is so-called shape angles, which determines the internal motion. It's interparticle position. Then wave function can be separated into this hyperradial part and this channel function part and rotational part. From now on, I'm concentrating on this channel function, this part, to see the particle correlation in an internal as in an internal motion. And a hyperspherical method, we can write this way in the kinetic energy part and adiabatic function, the total energy here. Then in the adiabatic eigenvalue problem is the eigenvalue problem from this adiabatic Hamiltonian. Then this is channel function and a potential, adiabatic potentials. Then take one of this, then just solve one channel approximation, then just approximation of the adiabatic approximation. Actually, this adiabatic approximation works very nicely for lithium triply excited states. Here, this is an example of triply excited states of lithium case. Then those whole bunch of curves are going to doubly excited states of lithium plus. Then triply excited states is those curves going to lithium plus doubly excited states. Then see those two groups of curves are border crossing is very sharp. Then we can easily to take one of them, then apply the adiabatic approximation. Then we can get this position. Then here is the experimental data is really quite complicated. But in adiabatic picture, okay, it's one-on-one correspondence here. This red one gives this resonance, and this is Rydberg series and ACDE. Then green one is from the second curve, and the blue ones is from this blue curve. It's quite worked quite very nice. Then of course
there's a fully developed Rydberg series within that red
yeah.
curve would there?
Yeah, of course, because in experimentally see low resolution, then they cannot see it. They cannot see it, but yeah, we can calculate. Just take one of the curve.
Where would the ionization limit be for on the experimental data? I mean,
which triply? I mean,
for the series on the red curve.
This red curve is around this, just below the F or somewhere. It's just somewhere. Now you see, they are not degenerate. Then there are many thresholds there. Then now you can couple all the channels, including those doubly excited states curve. Then we will get this not only the position but also the width. Here I calculated total energy eigenphase shift. Then here nice Lorentzian type curve here. Then blah blah blah. Then yeah, I see. Then just take here. Then experimental result is here. Then position the width. Then now we can couple all of them. But now it's not. I mean, so the problem is, your computer can calculate all the information, but how to classify those complicated triply excited states? This is what we are doing. Then we try to classify those triply excited states by using molecular-like modes. Then 3-electron nuclear, this system if you fix radial, actually the classical is all the 3 electrons is going to this nuclear but now if you fix radial distance from the nuclear, then here is the equilibrium position is triangle figure. Then what is molecular mode is one is rotation. It's rotate as a symmetric top. Then spectrum is like this way. Then another one is bending vibrational motion. Here is kind of umbrella motion of ammonia molecule, and here is the electron moving in a same plane. Then another type is a stretching vibration. This is kind of leading mode and this kind of motion. Okay. Then here is the energy level of n equals 2 manifold of triply excited states. Then this is from the independent electron model. You can see 2s2 2p, 2s2 2p2, 2p cube. Then it's kind of the order of the energy is like this. Then using the molecular modes, then we can see nice rotational picture here. This A is in this group, the internal motion are the same. Difference is rotation. Then here is the energy difference is follow this rotation of symmetric top. Then B is these group are different. The internal motion is different from the group A, but still again this rotational spectra is here, and C is another type of the internal shell, internal motion. Sorry. Then how can we see this? We have to see the wave function itself, not only the energy level. And to see the wave function, we take a little bit complicated variables here. Usually, intershell states principal quantum number is still okay. Then that means 3 electrons are almost at the same distance from the nucleus. Then now the important parameter is the angles. Then to specify the position of the 3 electrons, we need 3 angles, 3 relative angles. And here, first we define the plane where 3 electrons are on the edge of the sphere, edge of the circle. Then theta angle is the angle from this plane and this axis. Then on the plane, I took 2 variables. Then here, this eta is this angle between 1 and 2 from here. Then phi is the angle defined here. Then using these 3 angles, I can plot the wave actually density function like this way in a 3 dimension. Then we have to plot by the contour surface. Then here's the example of the contour surface. Then high density is inside of those things. Then this is the electron density of those A, B, C types I presented before. Really, in the same group, they are really similar electron density. Then, in terms of the molecular picture, here is the coplanar equilateral triangle. Then this B, here we can see the nodal surface here. Then this one, it corresponds to this ammonia type molecule. And here, this thing's nodal surface is perpendicular to the plane. And here corresponds to coplanar, this motion in the plane. Well, now I'm going to more excited states. I mean, at n equals 3. Then n equals 2, there are only 8 states, but here 64 of them. Then it's really difficult to describe described by the hyperspherical channel function. It's so many curves there. Then we try to understand by using Lee-Bender model, where 3 electrons are moving only on a sphere. Then parameter just split it to helium minus. Then here's the whole spectrum according to LS pi. LS pi. Then there, and n equals 3 manifold. In addition to this ABC basic mode, we have this excited motion, like indicated by these red symbols. Then AB, like many nodal surfaces appear in this sense, like this. Like AB is like a equilateral triangle is can allow here, but nodal surface here. Then here is kind of additional node here. Then those 64 states are classified by like those groups. And here is the energy levels according to the molecule-like modes. There also nice rotational structures here. But this model is quite good. It's not only a model. See, we can compare to this real calculation from CI. This is taken from CI calculation. Then its pattern looks the same. Then also in the real atom, there are really rotation molecule-like modes are there. So next, I'd like to show you about this intershell states. Now, one of the electron is in higher orbital, like 2 to 3. There, it's about 40, I think 49 or 50. I think 50 states here. Here's again, according to the LS pi scheme, the energy, it's like random. But in this case, the important thing is not only the angular part, but also radial part is important. Here is the intershell case where all the electrons are the same distance. Here is the counter map of the radial part. It's here at the center, which means that all the electrons is almost the same distance from the nuclear. But here, 2 to 3 intershell states. Here's nodal surfaces here, which means that the one of them is far from the nuclear. But still, angular part is the same. Then to classify those intershell states, we need, yet I think I think it's really well known asymmetry quantum number, which is introduced by Chidon. Then we have to have additional A, which usually A is symmetric antisymmetric motion in the 2 electrons, like going this way and going that way. Then we need additional symmetry. This A2 is the third one, between the third one and 2 electron of the electron core. In this case, 2 inner electron is moving, oscillate in the same phase. Then third one is also moving in the same same phase. It's kind of it's exactly the same as a bleeding motion. Then we call this A++. And here, 2 of them, oscillation of the 2 of the inner electrons are the same phase, but the third one and this pair is different phase. Like when these 2 electrons go closer, then the third one is go farther. Then here I put minus sign here. Then its total A is just plus minus. Then we need one more A here. Okay, by using these two A's, then here's the spectrum of the intershell states. Then this A, B, C are the same as the before, same as for the almost the same as for the intrashell state, 2, 2, 2 state. This is the angular part of the wave function. The difference is, again, it's in the radial part. Then this is A plus minus type is going this way. Then again, we can see really nice rotational picture here, rotational energy level here. Then B is phase in this, that means like a ammonium-like umbrella motion, but the third one is going far away. But here is oscillate in the same plane like this. Then this one is going that way. Then here, this, yeah, that's the motion of the molecular-like motion. Let me summarize of the classification of triply excited states. Yeah, principal corner numbers are still okay, but to describe angular correlation, we introduced this ABC type for the basic angular correlation, and also ABC, small ABC for the excited motion of excited states in angular variables. Then we introduced radial correlation. We introduced two A's to describe radial correlation. So now, moving to the four-electron system. Now, computer is so fast that I can diagonalize actually here three-dimensional problem. Then there are actually there are two ways to describe this hyperspherical coordinates, but I took just one of them. Alpha, beta, gamma, alpha, theta, like this way. Then diagonalize whole the adiabatic Hamiltonian. Then now I got this adiabatic potential. Again, the first one is going that bound state, ground state of this case is beryllium plus. Then this curve is going to beryllium, doubly excited beryllium plus, which means that triply excited somewhere here. Then now those curves are going to triply excited state on beryllium plus, which means that here see quadruply excited states are somewhere here. But again, the avoiding closing is so sharp, then it's really hyperradius. It's really good parameter as an adiabatic parameter. Then from this figure, we can say that this quadruply excited state is stable against to this decay channel. But this four-electron system is not only just additional electron. What interesting thing is there are two types of two equilibrium configurations here. One is pyramidal. It's like a spherical top. Then another one is planar. It's in the same plane. It's in like a symmetric top. Then okay, then if we classify, we can classify all quadruply excited states. There are two series of according to this pyramidal, spherical top, and a symmetric top. To finish my talk, I met a couple times, met Ugo Fano. Then really, for me, it's really amazing to see why so hyper-radius is nice, even in a four-electron system. Then I asked Ugo before, but he said it is obvious. Yeah, okay, for him it's obvious, but yeah, still I need to study more and more. That's all. Thank you very much.